Yes, we can hear you and we can see your slide.
Perfect. Thank you so much. Well, let me start by thanking the organizers. I'm pleased to see this is continuing as a series of workshops. There's a lot to be gained by the continuity that you have ensured here. So we've been working for the last few years to try to make robot grasping reliable. And I don't think I have to convince this audience that tactile sensing is probably a key part of making the sensing reliable. Now, the exact way to do that, however, is still very much up in the air. And I'll talk today about the approach we're following, which is very much old school. Yep, there we go. And in particular, we're interested in using analytical models. So nowadays, of course, the answer to every problem is to use machine learning. But we've gotten quite a ways in engineering across the last century by using deterministic models rather than data-driven models. And there's a handy set of models available for making grasping reliable. Typically goes under the name of grasp analysis. And this started way back in the 1980s. And I think the key paper, at least for me, is the Kerr and Roth paper, Analysis of Multi-Fingered Hands. And this has made a big impact in the grasp planning world. So I ran a quick Google Scholar search this morning, and the Kerr and Roth grasp planning has been cited thousands of times. But it's almost never been used for real-time control of grasping to ensure stability. So let me spend a minute and very quickly review the idea here. This is essentially Newtonian equilibrium. So the forces and torques applied to an object, taking into account friction, need to balance if your grasp is stable, and if not, there'll be some acceleration, there'll be some slipping. There are a bunch of different flavors of this. The original version assumes the grasps are with fingertips. That is, there are discrete contact locations. Shown in this little contact here is a two-finger grasp. And there are point contacts. And that mostly means there are no torques transmitted through the contact location. Now, these assumptions have been relaxed by various people. And in particular, Antonio Bicchi has come up with a number of interesting ways of dealing with more complex situations. But we'll stick with the original version here. And there are three things you need to sense in order to determine stability. The first is the contact locations, and the second is the surface normal directions. And you need to know the surface normals for calculating friction. So typically the analysis works in terms of a friction cone. So at your contact location, you have a surface normal vector. And as long as the tangential directions, the forces in the tangential directions, are inside this friction cone, you won't have slip. And if they exceed this, then you will see accelerations and slip will occur. And under the classic Coulomb model, during slip, this ratio of the tangential to the normal forces is the coefficient of friction. And we'll see in a second that this is, or by the end of the talk, that this is a somewhat dubious to very dubious assumption. And the last thing, of course, you need to sense here the contact force vectors. You need to know what the current loading is in order to predict whether you'll slip or not. Now, as I said, we've been surprised that nobody has implemented this much. This is maybe the most impressive implementation. And you can see this robot hand consists of three large industrial robot arms, each of which has a force torque sensor attached to these giant cylindrical fingertips, and you can see these robots are manipulating a basketball. And as far as we're able to determine, no one has actually tried to do grasp analysis for real-time control on a multi-fingered robot hand. Another favorite paper of mine in terms of grasp analysis is this paper by Ravi Balasubramanian, who's now at Oregon State. And he said, well, let's grasp a bunch of everyday objects and we'll shake them around and see if they're really stable or not. Meanwhile, we use grasp analysis to predict stability, and there are a number of different metrics you can use to talk about how stable things will be under various loading. And the conclusion was that, well, this grasp analysis stuff doesn't really work very well. But there was no force sensing here. So it wasn't clear what the actual forces were. And this is a Barrett hand. So it's a large metal very stiff robot hand, while some of the objects are compliant. So you can imagine if you take this box of crackers and you shake it back and forth, the actual contact forces are going to be changing a great deal because of the inertial forces and the compliance. So it's not exactly clear what was measured here or what conclusions we can draw from terms of grasp analysis. So we decided we're going to do this right, even if it kills us. And the idea here is we're going to make a system that's on a real robot hand where we can very precisely measure the contact location, surface normals, and the actual forces. And to do that, we started with the right hand robotics reflex hand, and we changed the fingers. And the biggest change is that this distal joint between the two finger lengths is a rubber bar. It's a flexure. And so that allows a great deal of compliance, which means this hand is good at generating passive stability. So if I go to grab something, the fingers kind of twist around and reorient to a stable location, and it works quite well. Unfortunately, it's very hard to sense the location of this distal joint when you're using these rubber flexures. So we've replaced them with regular pin joints, and we put angle encoders at both the base and the distal joints in order to use kinematics to tell us where the fingertip is. Now, behind each finger, we've mounted a 6-axis force-torque sensor, the ATI Nano 17s that are kind of a staple of robot research. And that gives us the XYZ forces and XYZ torques. And then the fingertips are hemispheres, and we'll see in a second why that's useful. Now, the crazy-looking sets of shiny balls up here are optical tracker fiducials. So this means whatever the resolution of our encoders, we can in fact get ground truth locations for where the fingertips are by using this optical tracker. And it's an Atraxis Fusion 500, which gives us about 90 microns resolution at hundreds of hertz. Okay, now the reason for the hemispherical fingertips is that this allows us to do intrinsic tactile sensing. Now, we built a number of different contact sensors to give us contact location, all sorts of different capacitive tactile arrays and barometer-based arrays. But we did some calculations. At the end of the day, we believe the most accurate technology right now is to use intrinsic tactile sensing. And this is something Ken Salisbury came up with in the 1980s. And it says, if I mount a 6-axis force-torque sensor under my fingertip, then I can use the relationship between the torque and the force and combine it with the equation for the shape of the fingertip. And here you see the reason we use a hemispherical fingertip is the expression for that shape is very simple. And then you can solve this equation in real time, starting with your force-torque measurements, and you can actually get the contact location at a very high rate. And our measurements suggest that the standard deviations of these measurements is something like 0.5 millimeter. So it's quite precise contact location information. Now, we also use this to get the surface normals, which again we need for calculating friction. And the shape here allows us to know the surface normal at the contact location simply because it's a hemisphere. And we use the fact that for two rigid objects, convex rigid objects in contact, the surface normal on one is opposite the surface normal on the other. So when we know the contact location on our fingertip, then we know the surface normal location on the object we're grasping. So again, we're interested in seeing how far we can go with these models if we have very precise measurements. So we need to do a lot of calibration. And one thing we need to know is the relationship between the surface, the spherical shape of the finger, and the coordinate frame for the force-torque sensor, and thus the coordinate frame for our optical tracker. One way to do this is to roll this fingertip all around on a flat surface, and then the center of the sphere should form a plane. And if we do that, here's some of the data from doing that. We fit a plane to this, and then that gives us the exact location of the center of the sphere in the ATI coordinate frame, and we're quite precise. This is something like 1/10 of a millimeter error for doing that fitting. Okay, so here's then a typical experiment we do. And you can see the fingertips are here with their tracking fiducials. So we have a thumb on this side and an index and middle finger, as we call them, on the other. And this is the object. It's a cube, and it also has these tracking fiducials. And there's also one here that's at the base of the hand. So we're able to relate all these locations to each other quite accurately. And if my video will play, oh boy, I'm afraid it's not. I'll describe what goes on here. So essentially, we pick up the object, we grasp the object, we pick it up a few centimeters and hold it. And after we're sure it's stable, then we keep pulling up. And there's a string that goes from the middle of the object down to the table, so that as we exceed the length of that string, the fingers are guaranteed to slip. We generate high shear loads on the fingers, high tangential forces, and the fingers start to slip. And here's some force data from a typical trial. We grasp, we get a good hard grasp, back off just a little bit, and then pick the object up. And this is the grasp force, the normal force, and this is the load force. You can see that as you reach the stable point, this is just the weight of the object that's supported here. Now we pull up against that string, the force goes up. At this point, one of the opposing fingers slips, and then finally the object drops back to the table and the forces all go to zero. And here's one of the strange things that happens. So this is the height of the object. It goes up. Again, we pull, and then it starts to slip. Here's an enlargement of it. You can see that as it starts to slip, the distance goes down. And then this is the velocity estimated from the position signal. This is the slip velocity between the fingertip and the object. Stays low, and then once we start to see slip, it has this jerky behavior, partly because we're estimating velocities from position signals, but also because there's the stick-slip phenomenon of the rubber against the object surface. Now, here's the force plot. And this is the ratio of the tangential force to the normal force. And again, here you can see it goes up, and then slip occurs. And this is the blow up. And so the ratio of the normal force to the tangential force remains the same before slip and after slip. It starts to bounce around here in kind of a crazy way. But this suggests that using the ratio of the normal to the tangential forces is not going to be a very accurate way of predicting slip. And the way around this, of course, is to be conservative and to say that, well, I need to assume it might slip starting at a much lower level. And so this forces us to be far more conservative than we really need to be in order to allow a grasp analysis to predict when slipping will occur. Here's another example of this normal force to tangential force, and this is a trajectory across time. So each of the little dots here is the normal force in the horizontal axis versus the tangential force. And you can see that, again, it's all over the place. This line should be the coefficient of friction, and under the Coulomb model, you should never see anything above that, especially during stability, but we see a lot of scatter. So the noise in the force sensor, or the complexity of the interaction between the fingertips and the object surface in parallel makes it very difficult to use these sorts of models to be highly accurate in your predictions. And this is the coefficient of friction, and this is the number you would hope to see the ratio between the tangential and normal forces while slip is occurring, and it's all over the place. We have nominally about an average of a 0.8 coefficient of friction, but we have numbers that are about half that and numbers that are about twice that are observed. Now, the implications for this are that we have to really back off on the coefficient of friction estimate that we use to predict stability. Now, a few years ago, we looked at how to relate tactile sensor resolution to stability. Now, you can imagine this is a two-finger grasp on a sphere. I put one finger at the bottom of the sphere, and then I say, where can I put the other finger so that I know I have a stable grasp? So if I have, say, a 30-degree tactile sensor resolution around my fingertips, I'm forced to use this region of the sphere as a stable grasping location. Down here, I know I'll be unstable, and over here, I actually don't know because of the uncertainty in my contact sensing. Now, if I improve the resolution, if I double the resolution, there's much more of the surface that I can stably grasp, and much less that's ambiguous. And this refers to tactile sensor resolution, but it also applies to coefficient of friction. That is to say, if I can assume I know the coefficient of friction, there'll be a much larger region where I know the fingers will be stable. Whereas if I can't assume that, I have to use a lower value, there'll be a smaller region. So this need for conservatism greatly restricts the kind of grasping you can do safely and be sure you won't slip. So let me draw some very preliminary conclusions. I want to be clear that this is work in progress. The instrumentation is very challenging to put together, and we're still working out the real-time control aspects of this. But it's clear to us anyway why people rarely have attempted to use grasp analysis in the past, and that's that it's really challenging to get all the instrumentation working successfully. And admittedly, this calls into question how practical this approach would be in the real world, where this kind of instrumentation is tough to get going. The other preliminary conclusion is that the inability to use a simple model like Coulomb to predict friction requires us to be pretty conservative in how this works. And a more informal observation is that a lot of the difficulties we're seeing here could probably improve by changing the design of the robot fingers. So, of course, the human fingertip is supremely compliant. You get a near uniform pressure distribution across the fingers, and this probably allows you to get far more repeatable frictional behavior. Also, the rubber materials we use, because they have nice high coefficients of friction, have this big problem with stick slip, with rapidly changing coefficients of friction. So coming up with materials that provide high friction but reliable friction could also probably make this approach work a lot better. Okay, so with that, I would be happy to take questions.
Thank you very much, Robert. I think Vincent has a question, right, Vincent?
Yeah, hi, Robert. Listening to you, I want to ask you a question that has tortured me for 20 years. Like when you talk about the coefficient of friction, you said, of course, the coefficient varies, and the tribology of materials is very unpredictable, etc. But there is another factor of uncertainty that I was already always answered about, never had an answer. The normal to a surface is rarely defined, actually, unless you have a perfectly smooth surface. If you take the coast of Brittany, the normal depends on how you, define it, and it's not a good concept, actually. So, and especially if your finger is soft, and so it's even worse, actually. So, what would be a good replacement?
Well, the only reason you care about the surface normal is for calculating friction. And this suggests that we need to think about this together. We need to think about the friction model and the normal definition together. Now, I'll say I'm not too worried about the surface normal issue you've raised. For our current experiments, of course, we're using lovely, perfect 3D printed spheres and cones and cylinders and cuboids. So we're dodging that particular problem. But I certainly agree, in the real world, it's tricky to define that. And people like to use corners. They like to use edges. I believe one reason is that it digs into the finger. You get an effectively some kinematic constraints as well as simple friction. And there, the surface normal is not defined. So what is friction in that case? I cannot answer.
So we have 2 more questions. Kevin. Hello, Kevin. Please.
Hi, Mohsen. Rob, thanks so much for your talk. That was great. I have a question about your ATI force sensors in your fingers. Those are quite expensive, and I think your group developed a cheaper flexure-based force sensor not long ago. I'm curious, are you moving in that direction, or is there a fundamental reason that you think they will not work as well? I mean, obviously the ATI sensors work well, but they're quite expensive.
Well, and you know, they have this amazing combination. They are both expensive and they are fragile. And we break one every few years. We're kind of overdue. And what are they, $7,000 a pop? Maybe we should be buying them in bulk. I don't know. Yeah, so we're actively pursuing this. We're looking, actually right now I have a couple students looking at how to build low cost, robust, but fairly accurate force sensors. And it's tough. We went with the ATIs because they're the best. And again, the whole impetus to this project is to say, suppose I have really good sensing, how far can I get using the grasp analysis model? So we are putting up with the expensive and fragile piece of this for the time being, just to carry through this thrust as far as we can take it.
Thank you.
So the next question, Yu She, right? I hope I can pronounce it correctly, your name. Yu?
Yeah, I'm Yu. Yeah, thank you. Yeah, thank you, Robert, for this very inspiring talk. Yeah, my question is quite related to Vincent's question. So in the first 2 papers, like grasping analysis and use geometry and the force to estimate the location. So those kind of theoretical model assumes maybe like a point contact, only one point contact. But as Vincent mentioned, in the future, we have a lot of like a soft finger or compliance contact. We kind of have a distribution contact, not a single point. So my question is like, do you have any insight how can we rely on those like point contact model to to help us understanding the distribution contact? Yeah, do you have any insight yeah, on that? Thank you.
So again, we're trying to keep things straightforward, not bringing too much crazy complication. But Antonio Bicchi just appeared on my screen, which is perfect because he did some work on soft finger intrinsic tactile sensing. And the big issue here is with point contact, of course, if I have a 2-finger grasp on an object, I can't resist torques, but clearly I am. If I did not, then this would simply pivot under gravity and I'd have a pin joint there. So it's clearly important in a lot of circumstances. Again, we are trying to keep things as possible just to see what the general approach can do. So for instance, because we have a 3-fingered hand, if we space the fingers sufficiently, then the torques generated about each fingertip will be tiny compared to the torque generated at each of the contact forces. And so that non-point contact contribution shouldn't matter, at least when we have all 3 fingers in contact and the spacing is much larger than the diameter of the contact at each finger. So what you've described, again, is very important in the real world when we want to get out there and do 2-finger grasps, that kind of thing. But for now, we're trying to simplify that away. We're trying to work in situations where point contact is a good approximation.
Thank you. Thank you very much.
So the last question, Huang, are you here?
Well, do you think like the coefficient is kind of the decision making, because it's I think in the real life is people is usually make the contact force by when they feel the slip on the finger, they will decision is how to make the contact force. And do you think is we don't have to care about the coefficient. We just like we have the problem like each robots will learn by themselves and they will decide how to make the fork to the keep for the avoid the slip when we grabbing, something like that. Do you think it's a kind of the decision making problem? It's not kind of the figure out how coefficient friction coefficient is working.
Okay, so let me see if I understood your question. So the Coulomb friction model has big problems. Can we do better with modeling? Can we come up with a better friction model? And you know, there are crazy complicated friction models out there, and they depend. You know, if you want to do it right with elastomers, you have to not only know the current conditions, the current shapes at the contact, the forces, the normal force, the shear force. You have to know the history, and you have to know what the loading was in the past to predict partial slips within the contact area. And once you start sliding, of course, you can generate heat from friction, and that changes the coefficient of friction for rubber materials as well. So I suspect at the end of the day, the win, though, is going to be to redesign the fingers. So you have nice, smooth pressure distributions whenever possible, and you have materials that give you a reasonable coefficient of friction, but much more predictable coefficient of friction than we get with our smooth silicone rubber fingers contacting smooth plastic object surfaces where you know, it's intrinsically complicated. But let me back up and say, I think at the end of the day, what you're going to get from a really accurate model is the ability to go closer and closer to that slip point. So if you have a really accurate model, you might be willing to go to 95% of the slip level for loading and know that you're still pretty safe. Whereas right now, I think you might get to 70% of the Coulomb predicted slip level and be pretty sure you aren't going to slip, you know, have a very high reliability. So the model will help, but at the end of the day, you'll always have to have some safety margin, and the better model will just make that safety margin smaller.
Okay, so thank you very much, Rob. Vincent, I think we don't have too much time, and we are 15 minutes behind the schedule. So,
all right, very good. So let's move on with